Study connectedness. In the study of calculus, there are three basic theorems about continuous functions, and on these theorems, the rest of calculus depends. One of them is intermediate value theorem, which states that if f is a mapping from closed interval ab to r, which is continuous, and if r is a real number between fa and fv, then there exists an element C belonging to closed interval AB such that Fc is equal to R. This theorem is used at many times, for instance in constructing the inverse functions such as cube root of x and sine inverse x. We have spoken of this theorem at about continuous function, but it can be considered as a theorem about the closed interval AB of real numbers. It depends not only on continuity of f but also on the properties of topological space AB, and this property is called connectedness. It is a fundamental notion in higher analysis, geometry and topology. Indeed, in almost any subject for which the notion of topological space itself is relevant. The definition of connectedness for a topological space is quite natural one. One says a space can be separated if it can be broken up into two globes, disjoint open sets. Otherwise, one says that it is connected, and from this simple idea, much follows. So, first of all, we define the notion of separation. Let X be a topological space. A separation of X is a pair of disjoint sets U and V, where U and V are non-empty open subsets of X whose union is X. The space X is said to be connected if there does not exist a separation. Otherwise, it is disconnected. So we can say that being connected is a topological property since it is formulated entirely in terms of collection of open sets of X. So first of all, we discuss one lemma. A space X is connected if and only if the only subsets of X that are both open and closed in X are the empty set phi and X itself. Now we prove this lemma. If A is a non-empty proper subset of X that is both open and closed in X, then the sets U equal to A and V equal to X minus A constitute a separation of X, for they are open, disjoint and non-empty, and their union is X. And conversely, if U and V form a separation of X, then U is non-empty and different from X. It is both open and closed in X. One more lemma. If U, V is a separation of X, then X is homomorphic to U union V. This symbol is used to denote the union of U and V such that U and V are also disjoint. Means U union V is homomorphic to disjoint union of subspaces U and V. If W is a subset of X and W is open, then U intersection W and V intersection W are open in subspace topology, topologies on U and V respectively. So W is open in U union V. Conversely, if W is open in U union V, then U intersection W and V intersection W are open in U and V respectively. Hence, these are open sets in X since U and V are open in X. Thus, W, which is equal to U intersection W union V intersection W, is a union of open sets because U intersection W is open, V intersection W is open. Hence, W is open in X. We have one more lemma. If X is equal to C union D with C and D non-empty, then CD is a separation of X. It is clear that C and D are disjoint, non-empty subsets of X whose union is equal to X. To see that C is open in the disjoint union topology, note that C intersection C is equal to C is open in C, and D intersection C is equal to phi is open in D. Similarly, D is open in disjoint union topology. A separation of a topological space X is a pair of disjoint non-empty subsets A and B whose union is X, neither of which contains any limit points of the other. In symbolic terms, we can write A intersection B bar denotes the closure of B is empty, and A bar intersection B is equal to empty, where A bar means closure of A. If A and B form a separation of X, then A is both open and closed in X. Since A is closed in X, therefore A is equal to A bar intersection X, and we know that the closure of A is the set A bar intersection X, and we can also say that A bar intersection B is equal to phi. Since A bar is the union of A and its limit point, B contains no limit point of A. A similar argument shows that A contains no limit point of B. Conversely, suppose A and B are disjoint, non-empty sets whose union is X, and neither of which contains a limit point of the other. It means A bar intersection B equal to phi and A intersection B bar equal to phi. Then since A bar is equal to A union A dash, so A bar is equal to X minus B, which is equal to A. Hence, A equal to A bar is closed and B is open. Similarly, B is closed and A is open. It means A and B are both open as well as closed and form a separation of X. Now we have some examples. Each one-point space is connected. One-point space means if X is equal to singleton set A, then it is connected because there are no proper non-empty subsets. One more example is of two-point set X equal to AB with Sierpinski topology TA equal to phi A X. The proper non-empty subsets of X are A and B because it contains only two elements A and B. Here the A is open because it belongs to topology TA, and second is closed because B does not belong to this topology TA. So A and B are neither both open and nor closed because A is open and B is closed. Hence, X is connected. There is no separation. One more example. Suppose X is equal to union of semi-closed interval -1 to 0. It is closed at -1 and open at 0. And another is open at 0 and closed at 1. So X is a union of two semi-closed interval and be a subspace of real line R. Each of the sets -1 to 0 and 0 to 1 is non-empty and open in X, although these are not open in the set of real number. Therefore, they form a separation of X, so X is disconnected. Here one may notice that neither of these contains a limit point of the other because 0 is their limit point. One more example, let X be a subspace of -1 to 1 of the real line. The set -1 to 0 and 0 to 1 are disjoint, non-empty, but they do not form a separation of X because -1 to 0 is not open in X. It is a closed interval. So it is not open in X. Alternatively, note that first set contain a limit point 0 of the second. Indeed, there exists no separation of the space -1 to 1. One more example. So, suppose X is a subset of Q, where Q is the set of rational numbers with at least two element is disconnected. Suppose P is less than Q belongs to X. If we choose a rational number A belonging to open interval PQ and we write U equal to X intersection minus infinity to A and V equal to X intersection A to infinity, then U and V is a separation of X, and it means Q is totally disconnected. Indeed, the only connected subspace of Q is one point set, a set consisting of only single element. A set consisting of two elements is totally disconnected. Now we have several examples of spaces that are not connected. How can we construct spaces that are connected? Now we shall prove some theorems that tell how to form a new connected spaces from given ones. So first of all, we prove one lemma. If the sets U and V form a separation of X and A is connected subspace of X, then A is a subset of U or A is a subset of V. So since U and V are both open in X, the set U intersection A and V intersection A are open in A. These two are disjoint and their union is A. If they are both non-empty, they would constitute a separation of A. Therefore, one of them is empty. Hence, A must lie entirely in U or in V. That is, A is a subset of U or A is a subset of V. One more theorem. The union of collection of connected subspaces of X that all have a point in common is connected. Suppose A alpha, where alpha belongs to J, be a collection of connected subspaces of X. Let P belongs to intersection of alpha belonging to J, A alpha. And let Y is equal to union of alpha belonging to J, A alpha. Now we have to show that Y is connected. Suppose that Y is equal to U intersection V, suppose Y equal to U union V is a separation of Y. Then P is in one of the sets U or V because P belongs to alpha belonging to J intersection alpha belonging to J, A alpha. So therefore P is in one of the sets U or V. That is, P belongs to U or P belongs to V. Suppose without loss of generality that P belongs to U. For each alpha belonging to J, the connected space A alpha must lie entirely in U or in V. Since P belongs to A alpha and P does not belongs to V, we must have A alpha is a subset of U. This hold for each alpha. It means union of A alpha, alpha belonging to J is a subset of U, that is Y is a subset of U. Because union of A alpha is nothing but Y. So it means Y is a subset of U. This contradicts the assumption that V is non-empty. One more theorem, the finite Cartesian product of two connected spaces is connected. Let X and Y be connected. Now, Y hypothesis, X Cartesian product of X and single sentence set Y is homomorphic to X, and Cartesian product of X with Y is homomorphic to Y, and these are connected because it is given that finite Cartesian product of two connected space. So this is X is connected and Y is connected. Now we need to show that their Cartesian product is connected. Suppose A belongs to X and B belongs to Y. For each Y belonging to Y, the space CY, which is the union of X cross singleton set Y, union A cross singleton A cross Y, is a union of two connected spaces with a common point AY. Hence, it is connected. It means X cross Y is equal to union of CY, where Y union varies over Y is also union of connected spaces with a common point AB. Hence, X cross Y is connected. This theorem may be this theorem we have proved for two spaces X and Y, but this theorem can be extended to n spaces. Any finite product x1 product of x1 x2 xn, which is x1 cross x2 cross xn of connected spaces is connected. We know that this theorem is true for n equal to 1, and we have just proved it for n equal to 2 in this theorem. The general case follows by induction on n using the homomorphism, because x1 cross x2 cross xn is homomorphic to x1 cross xn minus 1 cross xn, because we have proved it for n equal to 1 and n equal to 2. So by induction, this theorem can be proved for n spaces. One more theorem, if A is a subset of B and B is a subset of A bar, B subspaces of X, and if A is connected subspace of X, then B is also connected. Suppose that A is connected and we write B equal to union B is a separation of B. Because A is connected, hence A must lie entirely in U or in V. That is, we have A is a subset of U or A is a subset of V. Suppose we assume that A is a subset of U. It means B is a subset of A bar and this is a subset of U bar. Since U is closed in B, it equals to its closure B intersection U bar in B. Combining B subset of U bar and U equal to B intersection U bar, we conclude that B is a subset of U. But this contradicts the assumption that V is non-empty. Now one more theorem, the continuous image of connected space is connected. Suppose F is a mapping from X to Y and we assume that F is continuous And we also assume that X is connected. Now we prove that the image space Z equal to Fx is connected. Suppose that Z is equal to U union V is a separation of Z into two disjoint non-empty sets open in Z. It means F inverse U and F inverse V are disjoint non-empty open subsets of X whose union is equal to X. And they are open in X because F is continuous and non-empty because F is surjective. Therefore, they form a separation of Z. It means this contradicts the assumption that X is connected. Any map F from X to Y form a connected space X to a totally disconnected space Y. For example, a discrete space is constant. Since X is connected and F is continuous, its image Fx is connected subspace of Y as we have proved in this theorem. Continuous image of a connected space is connected. Hence, consists of at most one point. This means F is constant. Thank you.